Okay. So in Calc 1, you had ways of determining whether a point for which the derivative was 0 represented a relative max or relative minimum, right? And that usually involved what?
The test.
Whether it's positive or negative next to
Whether what's positive or negative?
this was next.
Like
Okay, and how did you do that? Well, first derivative test, and what did the second derivative test tell you?
Well, it also using
Concavity, right? Okay, so that's pretty much what we're going to do today. It's going to look a lot different, but it's the same idea. So let's just start with the picture,
Wait, why aren't we in two variables?
because we're not in Calc 1 anymore.
Like it means two in the like x as
Like f of x, y.
Oh, okay. I thought like for a second you meant like y. Okay.
No, that would be just one variable, yeah.
I could this is like 3 variables.
Yeah, let's just do that.
Sounds better if it's 3, right?
Yeah.
Okay.
Well,
So-
it's like just
X,
two,
Y, and
Y.
Z. It's not-
Here is a picture.
Is the shape erupting out of X, Y?
Yes.
Scenic countryside.
Thank you. Yeah, I tried.
Wait.
Wait, is that meant to be like all one?
This is all f of x, y, let's say.
Okay.
That's a
What
pretty
kind of
awesome
thing?
sketch.
Thanks.
I want to see.
So let's say this is a portion of f of x, y. This is stuff that we should already be able to talk about. Peaks are relative what?
Maxima.
Maxima. Valleys are relative minima. The highest max would be called the absolute max, and the lowest minimum will be called the absolute minimum. Again, if we're only looking at a portion minimum, if we're only looking at a portion of f of x, y, this, that, and that, all three of those would be considered relative maxima. Unless we had the whole picture, we could not say that either of these is the absolute maximum. However, if we're only constricted to this region here, then I think it's clear that this would be the absolute max. And then the other two would just be relative maximums in their neighborhood. Okay? And similarly, if we're restricting, then this would be the absolute min, assuming that we're only looking at this region. But again, if this only represents a portion of f of x, y, then we don't know much except that they're relative maxima or minima. Okay, so now here are some of the definitions that you need to be comfortable with. They're going to sound just like they did in Calc 1. Okay, so a function f has a relative max at a point x naught, y naught if there exists a, in Calc 1 it was like an interval, right? In Calc 3 we're usually going to talk about disks, okay, because we're not just going one direction, back and forth. We can go so let's say here's x naught, y naught, right? We can go any direction around that point. Okay, so that's what we mean by a disk. So if there exists a disk centered at x naught, y naught, such that f of x naught y naught will be greater or equal to f of xy for all xy in the disk. So this is just a fancy way of saying that for this point x naught y naught, if we're up here at the highest point, then this should be the highest output anywhere near this point. That's all that means. Okay. Now, similarly, a relative minimum, so I'm not going to write it all out again, we would need the output, f of x naught y naught, to be less than or equal to all the f of x y's in the disk, and absolute max would mean that f of x naught y naught will be greater or equal to f of xy for all xy in the domain, and an absolute min will be the exact opposite. The output will be less than or equal to all of the outputs for all xy in the domain. Okay, so these are definitions that should look familiar, yes, just in terms of two or more variables now. Okay. Any questions so far? Bless you.
Are you
Yes, I am recording,
just
but trying.
You said yesterday
Oh,
that you
yeah, great. Thanks for reminding me about 10 minutes in. Okay, so before we proceed, let's talk about bounded sets. Okay. In 2 dimensions, a set of points is bounded. Here's an intuitive way of describing it. If there is a rectangle that encloses, so let's say this blob represents the set of points. Okay? So if we have a set of points and we can put that inside a rectangle, we say that these points are bounded. Okay? Unbounded would be something like, I don't know, say all the points in quadrant 1. Because there is no rectangle that we could enclose all of the points in here, obviously, because we extend infinitely up and to the right. So this is what we'd consider an unbounded set. Okay, and the same holds in 3 dimensions. So in 3 space, instead of having a rectangle that encloses the set of points, we would have a what? A prism, cube, box, whatever you want to call it. So maybe we have some blob of points, a surface, and so anyway, if we have a point or a set of points in 3 dimensions, if we have a box that encloses it, such as this, we would say that this set of points, so here's our set of points, is bounded. Okay? Yes?
Is it like an actual box or is it hypothetical?
Well, I mean, it's an actual box. So like if you have a problem later on where they're saying consider only the values from 0 to 4 for x and for y, then we would consider that. Yeah.
But that's
What's that?
how it looks. There's no restrictions.
Well, it'll correspond to whatever heights in the z direction.
So like, just for example, if y is equal to x is unbounded.
Right. Yes. Yes. Question.
So, back to two space, is it, like, how is it unbounded if it's only, like, in quad one?
How is it unbounded?
Yeah, because, like, wouldn't unbounded be, like, every,
There's no.
Because
Well-
quadrant 1 goes on infinite.
Yeah, that's the reason
There's
why.
an infinite number of positive x's.
So even though we can describe it and say it's in quadrant 1, you could always extend to the right or up, and you wouldn't have any wall.
so we can't define the quadrant one as
You right, exactly.
Can you define
Define what?
it unbounded?
Unbounded just means that there's no end. Would be one way to think about it.
There's an infinite number of quadrant
Yes.
in that.
There's nothing. That's a good way to think about it.
Like it's an infinite set.
Right. Anything that's infinite is unbounded. That's the best way to describe it.
But so couldn't you have infinite points within a bound?
Oh, absolutely.
Yeah.
So that's maybe not the best way to describe it. Because even within the points, 0 to 4, let's say, there's an infinite amount of numbers between 0 to 4.
Let's do
But
You say it has an infinite domain.
let's just say all endpoints are defined.
aren't.
Well, for unbounded, it would be are not defined, yes. And bounded would be defined.
Like, this isn't meant to be, like, confusing,
Right.
This is
It's just pictures, people. Okay, so here's our goal.
Oh, we're not there yet?
Oh no, we got a lot more.
What?
Is this one with,
We have like 6 pages to get through.
Oh.
so,
The goal is going to take a line, so. To determine if there are relative extrema and to find their location. That's our goal. Okay, now before we get to the big thing for this section, again, there's several things we have to talk about first. So not only do we have to talk about what relative mins and maxes are, we have to talk about the extreme value theorem. Someone just got a text. You might want to. If f of xy is continuous on a closed and bounded set R, then f has both an absolute max and an absolute min. That's why it's important that we know whether we're dealing with a bounded set or an unbounded set. If it's bounded, then we have a guarantee by the extreme value theorem that there will be an absolute min and an absolute max.
if there are, like, if the highest point is, like, say, like, 2 points at the same highest point, is it just considered to have 2 absolute maxes?
It'd still be one absolute max, but then there would be 2 points that would produce that. So it wouldn't matter. Like if I asked you what is the absolute max, it wouldn't matter which one you use to get that, but just whatever that absolute max is.
Lines horizontally. Is it max is equal to min?
You mean if it's a plane?
Yeah, if it's like a horizontal
Then it would be the same. Yeah,
plane.
they could be the same value. Yeah. So going back to what we talked about earlier, let's say we're on the set from, so consider x being from 0 to 2 and y being from 0 to 4. And let's say over here,
Will we have to draw any?
no, not just for what's in the notes, just conceptually, so you can kind of see what. I mean, it's always nice to know that what calculations you're doing, what they correspond to, but no, you don't really have to like draw them. So let's say that's our, well, a part of our surface again. And specifically, that's the part of the surface that corresponds to x being from 0 to 2 and y being from 0 to 4. So this is a bounded set because we have explicit definitions for the endpoints of x and y, and there could be a box that would enclose all of the surface. But because we have a bounded set, we would label this point then would be the absolute max, and this point here would be the absolute min. Okay, now we will be interested in finding all of them, so all the extrema. Question is how we're going to do that. Okay, but first, another theorem, which should make sense back to Calc 1. If f has a relative extremum at extremum, extremum, at a point x naught, y naught, and if the first order partials of f exist at that point, x naught, y naught, then what should they equal? Yes. So if we were to take, let me use a different color. So if we were to take the derivative in the x direction or the y direction, okay, both of those lines would have slopes of 0. Okay? That's what this means. Yes?
Wouldn't they always exist at that point if there's an extreme?
Well, yes. But in order to do what we're going to do, not only do we have to have that point exist, we have to have that condition met first. Think back to like the first derivative test, right? The first thing you did in Calc 1 if you wanted to locate a max or a min was what? Take the derivative, set it to 0, because then that would tell you where, right? So the fact that you're doing that means that these derivatives exist in the first place. But wait, there's more. Remember this picture? Let me do my best here.
A saddle. Stop. Yay.
Is it? It only takes me a few tries, right?
I like.
I have like a way of drawing.
Wait, are we gonna find like saddle points and stuff now?
Well, that's the whole point. So
Oh.
here at this point, there's a few different things going on, right? So if we're looking at this point, I mean, it kind of looks like minimum or local minimum, right? But yeah, like depends on what direction you move. So for instance, if we go this direction, parallel to x, do you guys see that? It would actually be a max. But if we're going that way, right here, it's actually a minimum. Okay? So, partial x and partial y both equal 0 here, but it's neither a max or min. Again, the reason being, if you're sitting here at this point, if you come out towards us, what direction are you going to go, up or down? You're going to move down, right? But if you're going to start at this point and go left or right, you're going to travel up, right? So it's not a max or a minimum. That's what we call, so that's actually the definition of a saddle point. But we already talked about that because you guys were interested. But here it is again. All right. So now you have all the background that you need. You need to know what relative maxima, minima are. You need to know that the derivatives need to be 0 at these points. But you also need to know that we may not get a max or a minima. We might get a saddle point. Okay? So now we have to determine how we know which of those cases it is. Okay, so this is what we call the second partials test. This is like the analog of the second derivative test that you guys did last year. Well, we don't really call it that, but it would be setting the first derivative to 0 to figure out where are the points. We will, yeah. We'll do that and when we go through a comprehensive example here, when we put everything together. Okay, so the second partials test says that if we let f be a function of two variables with continuous second order partials in some disk centered around a critical point called x naught, y naught, and if we let capital D equal partial xx evaluated at x naught, y naught times partial y evaluated at x naught, y naught minus the mixed partial xy of x naught, y naught squared Let me make sure everybody has it right because mine is kind of smushed. Partial xx times partial yy minus partial xy squared. All three of those evaluated at that critical point. That's what we're calling D here. Okay? So that's the conditions that we need to set up. Now, if D is greater than 0 and partial xx at that point is also greater than 0, then we have x naught, y naught being a relative. What would you guys guess here? If d is greater than 0 and this mixed partial, or if not the mixed partial, but if partial xx is positive, that is correct.
Because it's the
It tells you about concavity and the extra, yeah. Mm-hmm. Now, no, I mean, you can just do the test and, yeah. It's not like the AP exam where, I mean, look, your grader is me and only me, so not that I'm saying you shouldn't show work, but obviously the more work you show, the more credit. No, but like if you know what you're doing and you could just do the test, then you're fine, yeah. Because I know what you're doing.
Wait, do you also grade on that?
Yes.
Wait, so we don't have like a test for this, right?
No, this is just, it's just a college class. Just like any other college class, you would take the final exam with that class. So you wouldn't like go to some other site necessarily. Okay, so now if d is greater than 0 and partial xx, oh man, I really messed up that. X naught, y naught. If that's less than 0, then what's x naught, y naught going to give us?
Wait, so D is still greater?
Yes. Then yes, we're going to get a relative max. So, because remember, there were 3 cases, right? Either we, well, actually there's 4, but if this calculation, if d is greater than 0 and partial xx is greater than 0, both positive, we get relative min. If d is greater than 0, but now partial xx is less than 0, we get a relative max. Well, what if d is less than 0? What is that going to mean?
Wait, so
Saddle.
Yes.
Wait, so the first two are both f of xx?
Yes.
Like, where did you get D from?
We just called it that, so I didn't have to keep writing it over and
What
over.
is that? Like, where did the people get that from?
It's kind of like a discriminant type thing. Like in the quadratic formula, it determines how many solutions there are, right? So we're calling this D because this determines what kind of maximum or minimum or whatever you have. What's the 4th case?
D is 0.
D is 0. If that ever happens,
Did it
we don't know anything. No, we didn't necessarily do it wrong. We don't know what it is.
So
Okay.
the test is
Yes.
Is there anything about f of y?
Good. I'm glad you asked. These are interchangeable, in fact. So if you prefer to do f partial yy, you can do that.
Okay.
So it doesn't. We just use partial xx because it comes before y. There's no.
Whichever one is easier to take.
Sure. Yeah. Yes.
Wait, what if partial xx is greater than 0 and partial yy is less than 0?
That will never happen for these 2 cases, and I'll explain why. That's a great question. So, in order for this to be positive, right? Keeping in mind that we're subtracting a number, because this is a square, so we're always subtracting something from that, right? Then this must be positive. And if this is not only just positive, but it's got to be bigger than that, right? But if this is positive to start with, then that means that not only is this positive, but these 2 have to have the same sign. So either both plus plus or both minus minus, which actually kind of explains what you were asking. Doesn't, it won't make a difference which one you use because it'll tell us the same thing. Okay? So let's try to put some stuff together, shall we? Oh, should I prove it? I got a 2-page proof ready to go.
Yeah.
If you don't make us prove it on the test, then okay.
No, just don't. Just
Hey,
wait
what?
until like Brandon's here.
Wait, prove what? That D equals
To prove why this whole partials test actually tells us what it tells us.
Do it.
You would never, ever, ever have to do this on an exam because it's just really long.
Let's do it.
Let's do it.
Yeah.
How about if there's time, I'll go back to it. Let's get through some of the examples first.
Kevin's gonna mess up the order.
Wait, can
Yeah.
you just prove that D equals that thing?
Well, basically, okay. Here I can kind of tell you what we're gonna, if we do prove it, how it would look. What we would have to do is actually bring back in the directional derivative,
Oh.
because we're going to generalize this and say that it doesn't matter which direction you look at, that if we have concave up or concave down, then this needs to happen in any direction. So we would do the gradient and bring in the unit vector, and then also apply it one more time to get the second derivative in there to talk about concavity. And then that produces a whole bunch of cases. In part, this little d thing pops up, and that's where these cases come from. Okay, so anyway, if there's time, we'll go back to that. It's not huge. I don't even think it's in our book, to be honest. So,
Did you just prove like yourself?
I had a outline for it, but yeah, I consulted other resources. I'm not going to say, oh, it's not in the book, I'll just do it. No, because I want to, give you something that actually is legit. So, okay. Let's try this example. Let's say f of xy equals negative x cubed plus 4xy minus 2y squared plus 1. And we just want to find the relative extrema. Okay, so first, we need to find critical points. Where are we going to do this test, right? And to do that, we do what we did in Calc 1, which is find the, partial, but which partial?
Where it's
The first partial, set it to 0 and see what happens. So,
wait, the partial of x or y?
both. Because if we just do x, what do we get?
Just the X. You don't know if it's good.
Well, we get negative 3x squared plus 4y, and if we set that to 0, there's an infinite amount of times where that's going to be 0, right? So that's not specific enough. But if we take partial y and also set that equal to 0, what do we get? Which produces a system that you have to solve, yes.
You just add them.
Oh yeah, if you add them, that's nice and convenient. If you add them up, you get negative 3x squared plus 4x equals 0. So x is pretty easy to solve for. Factor out the x, we get 3x minus 4, which leads us to believe that there are two x values, right? X equals 0 and 4/3. So now each of these x values will correspond to a y value. Now, I think you can gather from this second equation that x and y are the same, right? So if x is 0, that means y is 0, and if x is 4/3, that means that y will be 4/3 at that point. Okay? We good on that? So we have two, and here's kind of how I do it. We have two critical points. So I'll put those over here, and we're going to do a little table. So 0, 0, and then 4/3, 4/3. So these are the critical points. And now here we'll set up a D column. And then over here we'll write down what's going on with partial xx. And then over here we'll do the conclusion. Okay, so, but in order to do d in partial xx, we have to do more calculus. So,
Wait, why did you choose y equals x?
I didn't choose y equals x. It needs to be y equals x because the second equation, right, if you look at how it's written, if you solve for y or solve for, you're going to get that y has to equal x. Yes?
Why did you pick fxx? What why?
That's what Priya asked about.
It doesn't matter.
Oh, I was just thinking that's why looks like it.
You can do it that way. I'm just going to keep things consistent so that if you were to consult another source or resource, they're going to do it pretty much the same way. So, okay. So partial x we already have. Partial y we already have. Partial xx will be negative 6x. And partial yy will be negative 4. And partial xy, the mixed partial, will be 4. Okay? So then now d, remember, d equals partial xx partial yy minus partial xy squared, if you forgot it, right? Plug in these values, 0, 0, into partial xx and partial yy. What are you going to get? You're going to get, well, negative 16, right? Because negative 4 squared. Here, partial xx is what? 0, but it doesn't make a difference. Because if d is less than 0, what's the conclusion? Saddle point.
Are saddle points actually that common?
Yeah.
So is saddle
We can probably, yeah, we'll put this up when we get a chance. 4/3, 4/3. All right, so let's do the same thing. Plug it into f sub xx, f sub yy, subtract. What are we going to get? Let's see. Well, we're going to have negative 6 times 4/3, and then just times negative 4. And then we're going to subtract again, 16. That's 32 minus 16, which is positive. So now we do want to inspect partial xx. Partial xx at 4/3 is negative, right? It's negative 8. So just keep track of your cases. Positive, negative means relative what? Good. And now this is pretty much all you would say. 0, 0 is a saddle point, and 4/3, 4/3 is a relative max. Well, if they asked you, you could test the points and see what.
Oh, wait,
which
but
one gave you
if
Right.
4/3 is the only relative max.
Then it would be the absolute max, right? The point is, a lot of times we don't really care. I mean, we do care about the outputs, obviously, but we know how to do that. What we're more interested in is locating what x and y have to be to produce those things. So if they ask you to discuss the relative extrema, this is enough. This input's the saddle point, this point's the relative max, and we're done. If they, rarely will they, but if they do ask what is the absolute max or the absolute min, or what are these values, then you just plug them in. You guys know what I mean, right? Plug these into f of xy, and you'd actually calculate what z would be. Okay? If that's the case. This is actually a good place to stop. So you should be able to do a pretty significant amount, I think, of the homework over the weekend. I would advise you to catch up so that we can go over questions if need be. Tomorrow, when we come back on Tuesday,